how do we explain the trend in ionization energy? What you need to do is examine your valence electrons and use Coulomb's law. In general, remember it's the valence electrons that you need to get rid of, that will be lost by the atom when it ionizes, right? And we talk about ionization energy. So the farther that valence electron is from the nucleus, that means the weaker the inward pull on that electron by the nucleus. So it's going to be pulled into the nucleus. The nucleus is positive, the electron's negative, right? It's going to be pulled towards the nucleus. But so if you want to remove it, the farther it is from the nucleus, the easier it is to remove. Remember, Coulomb's law says that the force is inversely proportional to the square of the distance. So if you double the average distance from the nucleus, you're going to quadruple, and you're going to cut the force that's holding it by a fact to a quarter of what it is. Okay. Now the other factor depends that the attraction depends on is the nuclear charge. So the more protons you have in your nucleus, the stronger the pull on those electrons in the valence electron towards the nucleus. Okay. And then the other thing you need to consider is within that valence shell, okay, there's going to be other electrons that's going to partially shield each individual electron from the pull of the nucleus. So there's going to be repulsion from the other electrons. In other words, let's say you have 2 protons in here and you have 2 electrons out here. Okay. Now each individual electron out here is not going to feel the force of the 2 protons because it's going to feel a repulsion from another electron. So we say each electron in the outer shell will experience what we would call an effective nuclear charge, and that's what you need to examine to explain the trend. Okay. So how do you explain the trend going left to right? As you go from left to right, okay, your outermost electron on your periodic table, your outermost electrons will be in the same valence shell. For example, let's just compare lithium versus beryllium. Okay, electron configuration of lithium is 1s2, 2s1. These are the elements in the second row, and your beryllium would be 1s2, 2s1. Okay, 2s2. Sorry, 4 electrons. So this has a core 3 protons in the nucleus, atomic number 3. It has 2 electrons in the core. Okay, and you have that 2s electron, 1 electron in the 2s orbital. So 1 electron out here. Compare that with beryllium, which has 4 protons in the nucleus. It has 2 electrons in the 1s in the core, and then you have 2 electrons out here. Okay? So going from left to right, you're going to have more protons. So you would expect that the inward pull due to the protons will get stronger as you go from left to right. But there will also be more electron repulsion. Here you have an extra electron in the second shell that would repel that other electron. So that counteracts the effect of the 4 protons. Okay? But if you look at the direction of the force, the force due to the nucleus is always directed inward, whereas the force due to the other electron is not always directed inward. Okay, so like if you have an electron here and an electron there, the repulsion would actually tend to push it outward. Okay, but if the other electron happens to be here, it could push it a little inward. So the shielding then due to the other electron is not going to be complete. Right? So we say that the charge of the nucleus is only partially shielded by the other electrons. So 1 additional proton in the nucleus and 1 additional electron in the valence shell simply means there's a net increase in the effective nuclear charge, because that additional proton is not going to be fully shielded by the additional electron. So going left to right, then we can say left to right, you're going to have an increasing effective nuclear charge. And that pretty much determines the trend going from left to right. As you go from left to right, your outermost electron okay, we'll be feeling a much stronger force, okay, due to a higher effective nuclear charge pulling it into the nucleus. So if it's going to feel a stronger force towards the nucleus, it's going to be a little harder to remove it from the atom. So the trend from left to right, okay, of increasing ionization energy is due to a stronger effective nuclear charge as you go from left to right. Like I said, there are exceptions here and there. For example, if you're going from beryllium to boron, the electron configuration of boron is 1s2, 2s2, 2p1. Okay, it's actually a little easier to remove the electron from the 2p orbital as in the case of boron. Okay, so the ionization energy actually drops as you go from beryllium to boron. But the general trend from left to right is increasing. I'm sorry, that's a 2s2. How do we explain the trend going from top to bottom? The trend is, explanation is pretty simple. As you go from top to bottom, you're filling in, your outermost electrons will be much farther away as you go down a groove. Okay, so the pull from towards the nucleus is going to be much weaker. If you remember, Coulomb's law says that the force is inversely proportional to the square of the distance. So if you double the distance, so if you double the size of the shell, okay, you double the average distance from the nucleus, the force of the nucleus that's pulling in that electron towards the nucleus is going to get cut by to a quarter of what it was in an inner shell, okay, in a shell that's closer to the nucleus. So you're looking at more or less the same effective nuclear charge, but as you move further away, you're going to see a significant drop in the force on the electrons on the outermost shell. So that explains the trend in ionization energy going down a group. So for example, lithium is 1s2, 2s1. Compare that to sodium, 1s2, 2s2, 2p6, 3s1. Okay. This electron in the second shell versus that electron in the third shell, this is going to be much easier to remove. It's going to take less energy to remove that electron. It's farther away from the nucleus than the 2s electron.